Good evening, everybody. Welcome to session 6 of our custom types module. Did a few people put their hand up when they said they're here for the first time? All right, well, quite a few of you. Hello and welcome. So for those who did just put their hand up, are you sort of completely new to C++? Have you got a bit of a background to some programming? Nodding C++, used it before. Yeah, we done some C++. So okay. What about over here? Are you guys sort of completely new to this, or are you? Okay. So you've decided to hop onto this train instead. Okay. The reason I mention this is because for this year, for 2020, we're trying something a bit different, something we haven't done before, which is to basically have two streams that alternate on a weekly basis. So last week and next week and 2 weeks after that, we've got our sort of nice, gentle beginner track, which is aimed really at people who haven't done any or very much programming. And we take things kind of nice and gently and explain things very gradually as we go. And then on the alternate week, so this week, 2 weeks from today, 2 weeks after that, etc., it's aimed more at people who already have a bit of a programming background. So you know what functions are, you know what variables are, you perhaps know what classes are and these kinds of things. So we can move along a little bit quicker and really get into telling you about perhaps more about how C++ might differ from the programming language you already know, and how the concepts that you know map onto C++. Okay, so again, this is sort of an experiment. It's sort of the first time we tried it. People have suggested it in the past, and we're trying it out for this year, having these two streams. So yeah, this class that we're on now, the subsequent one will be 2 weeks from today, and then 2 weeks after that, and 2 weeks after that. If you're one of the new people, or even if you aren't, if you find this is all a bit like, oh my God, I don't get it, this is all kind of way over my head, then of course you're more than welcome to switch to the other stream and come on the opposing 2 weeks, if you see what I mean. And you might find that a bit more easygoing. Okay, is that clear to everybody, right? What we're aiming to do, at least. We'll see how it goes. I mean, as I say, it's kind of an experiment. We'll see how it goes. Reassess after a few months whether it's working or not. Okay, for those who have been here many times before, will have seen this first slide that I put up at the start of every session, which is to say that we love to hear from you. We love to know what we're doing well. Obviously love to know what we're doing well. Also, equally important, more important perhaps, is we need to know what we're not doing so well, what's not working. One way to do that is you can email us. Email's on our website, admin@cpplondonuni.com. But a sort of easier, quicker, faster way to talk to us and to everybody who's involved in the group is to jump on Slack. So Slack's a very heavily used chat application for those who haven't heard of it, really heavily used in the programming world. There's a CPP Lang Slack organization. This is it's not run by us, but it's got 10,000 members, I think, all around the world discussing the C++ language, and we have our own little chat room inside this that we kind of use and piggyback off. So everybody's welcome and very encouraged to join our Slack group. Just go to that URL that's on the screen, slack.cpp.al. There's a little form on there, and it will send you an invitation to come and join the CPP Lang Slack. As I say, we've got our own room in there. There's also another room that's #learn that is a really, really great resource. If you're learning C++, there are learners from all around the world, not just for this group, but from all around the world, and lots of experts who sit in there and really like to give really helpful advice for things you're stuck on, questions you might have. So this is a really, really great resource, and we encourage everybody to make use of it. Okay, so who was here 2 weeks ago? Last time we were talking about this stuff. not all that many of you. Well, okie dokie. All right, so last time, well, this whole module has been about writing your own types, structs and classes, your own data structures, your own data types. That's what this whole 5 weeks so far has been about. And last time in particular, we talked about aggregate types. We'd already mentioned constructors in the previous week. We talked a bit about constructor overloading. And we talked about default constructors and defaulted constructors and how you can write those. So if this is your first time on this module and you want to catch up, all of the previous videos are available on our YouTube channel, youtube.com/cpplondonuni. You'll find videos for going back a couple of years, but in particular, if you do it in sort of data order, you can go back and see the video from all of the videos for this module. And the slides also should be available, only I'm a fool and forgot to do it, but they will be available on our GitHub page. That's github.com/cpplondonuni, and you'll find all the slides from the previous sessions. Except the last one, because I kind of forgot. Sorry about that. Oops. So this week, because I kind of anticipated we might have a few new faces, we're going to do a very brief bit of revision for what we covered 2 weeks ago. 2 weeks is kind of a long time, so we're going to have a brief bit of revision. And the main thrust of what we're going to do this week is we're going to talk about explicit constructors, and then we're going to go on to talk about member initializer lists. And in particular, if you're familiar with sort of Java or C# or whatever, and you think, oh yeah, constructors, I know all that, I'll just switch off. Well, these are things that member initializer lists in particular that don't really, or are not in Java and C#, so might be a bit new for everybody, something kind of peculiar to C#, sorry, to C++. All right, so that's the plan for this week. So that sound all right? Thank you, John. All right. So first thing we're going to talk about very briefly is just something we mentioned a couple of weeks ago, but it's kind of important, and again, it's something kind of peculiar to C++. We're going to talk about this notion of aggregate types. So actually, perhaps somebody can tell me, what's the difference between a struct and a class in C++? Yeah, so probably didn't come out on the microphone, but in a struct, members are public by default, that is, unless you override it. In a class, members are private by default, unless you override it. It's one of only two, that's the main difference. There is another minor difference people always forget, is to do with the default inheritance level, but the main difference, the main thing you have to remember is struct members are public by default, class members are private by default. Other than that, structs and classes in C++ are identical. There is no difference semantically between a struct and a class as far as the language is concerned. And this is quite different from, again, how other languages work. So there are other languages that have both structs and classes. C# is one, Swift is another one, D, if you know D. They have structs and they have classes, but they work quite differently. Generally, structs are value types and classes are reference types. Well, in C++, structs and classes are the same thing and they're all value types. But C++ has this notion of something called an aggregate. And an aggregate basically is a really simple struct or class, because they're the same thing. Really simple struct or class where all of the members are public and there are no constructors. All members public, no constructors. There are a couple of other, if you really get into it, a couple of other conditions, but these are the ones you have to remember. No constructors, or no user-defined constructors, and only public members. And aggregate types are a bit special. And they're sort of in the language, as far as I can gather, as a sort of legacy of C compatibility. So C++ started out as C with a bunch of stuff added to it. And the two languages have evolved separately, but C++ maintains a level of C compatibility. And aggregate types are part of that. So for most of our classes, when we create an object of that class type, we do so by invoking a constructor. It's mainly what we've been talking about for the last couple of sessions, is constructors and how we write what they do. Well, aggregates have no constructors. No user-defined constructors, at least. And so the way we construct aggregates is by directly setting the values of the members. Because all the members are public, we can just directly access them, directly set them. This is a special kind of initialization. It's called aggregate initialization. And in fact, until a couple of sessions ago, when we started talking about constructors, everything we had used in the course up till then was actually secretly an aggregate. I just hadn't told you that we were in fact using a special case. Right. So, as I mentioned, structs classes exactly the same in C++, mean the same thing, just the defaults are different. However, there are some style guides, some kind of company internal coding guidelines. Because C++ is such a flexible language, there are lots of different equivalent ways to do the same thing, and so lots of companies have their own coding standards, their own style guides. Doesn't just happen for C++, happens for a lot of languages. But there are, it's one of the common elements that you will see in style guides is that they suggest that even though they're equivalent as far as the language is concerned, it's the suggestion that you should use the word struct only for things that are aggregates, for more or less C compatible or C style structs. And if your type is more complex, if it has constructors, if it has private members, perhaps it has base classes and virtual functions and all that stuff, then you should use the class keyword. Now, whether or not you follow that advice is up to you, but this is, I'll mention it because it is quite common, and if you go browsing any sort of public C++ code bases, you might see this rule in action. But always bear in mind that struct and class mean the same thing. So this is a very canonical example of what we mean by an aggregate. This is struct. Struct's members by default are public. So the two members here, the int I and the float f, they're public. This has no constructors. This thing is an aggregate. In fact, in this particular example, is C compatible aggregate. All structs in C are aggregates. There are other ways we can write this, or we can write something similar. We can use the class keyword to introduce a type. So this is a class, but all members are public because we've immediately opened the public section. So all members are public, and it has no constructors. So this thing is an aggregate even though we've used the class keyword to define it. It's still an aggregate. Is this thing an aggregate? Is example 3 an aggregate? Why do you think it's not? Exactly right answer. So classes default to private member access. And we notice this one has the public keyword here. Example 3 doesn't. So the two members here are private. So this thing is not an aggregate. Remember, the conditions for an aggregate are no constructors and all our members are public. In this case, these members are private, therefore example 3 is not an aggregate. Yes?
I would like to ask the second example.
Yeah.
certain parts public.
Yes.
But the rest is not public, just the.
So once you've once you've written public with a colon after it, everything that appears after that is public until you use the private, or there's another one, protected as well, that we'll get onto in a few weeks' time. So you can have public, private, and protected, and you can mix and match these however you like. You can have some public members, some private members, some more public, protected, some more private. And you can mix and match them however you like. Okay.
So hierarchy can be defined in access levels.
So there are precisely 3 different access levels, right? Those are public, that means anybody can access it. Private, which means only members of the same class can access it. And there's a third one called protected, and that's to do with inheritance, and it means that only derived classes can access it. Okay, but we'll get on to talking about inheritance and all that stuff. That's going to be the next module, in fact. So for now, yeah.
One question. So when you have a structure in a class,
Yep.
the same member variables,
Mm.
and I declare all of them public in the class,
Mm.
would it actually compile, like the compiler, when you look at the 2 different compilations, exactly be the same on the byte level? Or is it just in theory the same?
Okay, that's a good question. So the question is, if I have, well, let's not even worry about struct and class. Let's say if I have 2 structs that have different names, but have the same members in the same order with the same names and everything, these 2 structs are byte for byte identical, right? If they have the same value, then their byte representation is identical. But as far as the language is concerned, they are different types and they cannot be mixed. Right, so C++ is a strongly typed programming language. There's a term for it. I think it's nominally typed. So unlike, say, something like JavaScript, where you would be able to, if they have the same, if your members have the same name, they don't call them members in JavaScript, do they? But if they have the same name, you can sort of use them interchangeably. That's not the case in C++. If we had, so if example 2 here had int I and float f, they would have the same representation, but they'd still be different types. But that's a good question. But you can't have a struct and a class in the same name.
Memory-wise,
Sorry?
location memory-wise should be different, shouldn't it?
Location?
Allocation, memory allocation. Because you say that there is no constructor. So either there is a hidden default constructor or there is no constructor.
In terms of the memory allocation, so when you create an object of this type, of say example 1, what it is going to have is, in this case, it'll have 4 bytes for the int, 4 bytes for the float, and that'll be it.
Right.
Yeah. And if you use the class keyword, well, your memory layout is going to be exactly the same. It's not going to alter.
So when you, there is no constructor anyway in the structure.
There's no constructor.
Unless it's a default constructor, so you cannot it's not a class. So when you instantiate the class, there would be the default constructor called, and therefore there is no difference in terms of memory.
There's no structs and classes are the same thing. There's no
sorry, aggregate. Sorry, I meant aggregate.
aggregates.
I mean aggregate, not struct. Sorry.
Yeah.
I meant aggregate in my mind.
So in terms of memory layout, so all the constructor does is initialize the members, give them their initial values that we'll see in a minute, and perhaps do some work in the constructor body. But in terms of the memory layout of the class, it's no different whether it's an aggregate or whether it's a class with a constructor. Yeah. Okay, so example 1 is an aggregate. Example 2 is an aggregate, albeit in a form that you don't see very often, but it is still considered an aggregate. Example 3 is not an aggregate because the members are private. And perhaps I could add an example 4 where all the members were public, but we had a constructor, and that wouldn't be an aggregate either. So I went through these last week, and if you want to have a more thorough treatment, the video is available. But we can use what we call aggregate initialization with example 1 here. So in the first case, remember with aggregate initialization, we're directly setting the values of the members when we construct the object. So here we're directly setting I to 1 and F to 2, 2.0. And this, the first line, is the form that you will see in the C language. That's the way it's done in C, and C++ can use the same syntax if you like. You're also, in C++ at least, allowed to omit the equal sign to just just have the variable name and then a curly braces. With aggregates, you don't necessarily have to supply a value for each member. In this case, we're giving a value for the first member, I. We haven't supplied a value for the second member, so that's going to be what we call value initialized. It's going to have the value 0, because it's a float, and the default value for floats is 0. And in the third case, what's happening here is, well, we haven't supplied either of the values, so they're both going to get their defaults, which for an int is an int of value 0. For f, it's a float of value 0, so they're both going to be 0. No, you don't in this case, as far as I know.
What about if you supply, like in the first case, you supply a different type from what expected from the declaration?
Well, we can actually see that in this case. So here we've got, still an aggregate, remember, we've got two members, a string and a double. And we're initializing this with a string literal of hello, and this is a double. Well, in this case, string literal is not the same type as a standard string. A string literal is a funny thing in C++. It's an array of characters. It's not a standard string. But what the compiler does is it creates a standard string from this literal that we've supplied. So this is going to work just fine. So in this case, this isn't the same type, but it's a compatible type. So the compiler does the conversion, and everything works the way we'd like. In this second case, again, we're omitting the second value. We're not supplying the double this time. When we did that last time, well, the float got default initialized to 0. In this case, we supplied what we call an in-class initializer. We'll talk about these, or see these again very shortly. But we've supplied a default value in our class definition. So what we said is, okay, if the user doesn't supply their own value, I want you to use this default value instead. In this case, sort of very bad approximation to pi. So in this case, str is going to be hello again, and d is going to have the default value from the in-class initializer of 3.142. What we can't do, at least until C++20 comes along, is to omit str. So when you use aggregate initialization, you have to initialize the members in the order that they appear in the class. So we can't omit str and just try and set the double. That's not going to work. What it's going to try and do in this case, is to go, okay, I'm going to see if can I convert a double into a string somehow? And no, it can't. we hope. So it's going to give you an error saying, okay, well, you asked me to do this, and what I interpret this as meaning is, please try and convert this double into a string. I don't know how to do that, so that's going to be a compile error. Yeah.
If I just put a how do we call it, colon, or to separate the comma, is it acceptable?
So if you just put a comma in the front, no, that wouldn't be. But what you could do is just, if you wanted to, you could put just an empty pair of double quotes, and that would say, okay, just make str an empty string.
Then comma and the rest.
Yeah, yeah. So last example, well, we've already decided example 3 is not an aggregate. Done. So what's going to happen in this case? Well, we're going to get an error. I'm not sure of what the exact error wording is, but basically what it comes down to is you're trying to use this as if it were an aggregate, but it's not. And so the compiler will say something along the lines of no matching constructor. But rather curiously, this final one is going to work. Which is a little bit strange, perhaps, because we haven't defined any constructors for example 3, and it's not an aggregate. Sorry?
There is a default one.
There is a default one, yes. It's a hidden compiler-generated default constructor. We'll talk more about those very, very shortly. But let's just very briefly talk about constructor overloading. So in C++, we can have multiple functions with the same name but different parameter lists. We call this function overloading. Right, this is quite a common thing to do. It's not something a lot of languages do, actually, but C++ does. And in the same way that we can have multiple overloaded functions, it's possible for a class to have multiple constructors with differing parameter lists. Okay? This is very, very common. In fact, it's it'll happen anyway. Even if you do nothing, you'll automatically get several different constructors. So we can have multiple constructors with different parameter lists. And what happens is that when we create, if we have a non-aggregate, this is so an ordinary class with constructors and stuff. When we create an instance of that class, the compiler is going to look at the arguments we supply, and it's going to try and match those to one of the constructors as best it can. Right, so it's going to look at the arguments we supply, look at the types of those arguments, look at the number of arguments, and it's going to find the best matching constructor. Okay, this process of analyzing the arguments and matching them against the candidate functions, this is a process called overload resolution, which is when you really get down, it's fearsomely complicated, and it strikes fear into all of the C++ standards committee people. Right? Overload resolution is really complicated in the details, but by and large, 99% of the time, it's complicated because it tries really hard to do what you expect. The overload resolution process for selecting constructors is, fortunately, one of the rare cases where C++ gets it right. The overload resolution rules are exactly the same for selecting constructors as they are for selecting function overloads. So that's, at least there's only one set of rules you have to memorize, even if those rules are very, very complicated in terms of the sort of the nitty-gritty of them. But let's just have a look at a class that has multiple constructors. So we've got a constructor taking 0 parameters. A constructor taking a float. And then we've got a private, the radius member of our circle class is private, right? So nobody else can access it. So this class has 2 constructors, 2 user-defined constructors at least. Constructor taking no parameters, and a constructor taking a single float. And so when we create a circle, well, we've called this with no arguments here. So this is going to look at the available constructors, and it's going to say, okay, well, this one's expecting a float, this one's expecting nothing, you've supplied me nothing, so I'm going to call this guy. Right? And what this does is it prints out calling circle, empty brackets, and sets the radius to 0, which is kind of redundant because that's what it'll be anyway, but you know. Second example now, we're constructing a circle and we're supplying one argument, which is a float value 3. And again, the same process is going to happen. The compiler is going to look at the what they call the candidates, candidate constructors. Well, it's got this one that takes no parameters, but we've supplied one. Okay, so that one's out. You supplied me a float. This one's expecting a float. Well, that's a perfect match. So I'm going to call this one. And this is going to print calling circle brackets floats. And then it's going to do this thing of making sure that the radius you've given me is positive because, as we've mentioned in previous editions, when we were using this, iterating on this circle class, you know, having a circle with a negative radius is kind of doesn't make any sense geometrically. So we want to make sure that the initial radius is greater than 0. Later on, we'll see how we could throw an exception if this were not met, which was usually what you would do in such a case. Finally, let's just create a string, a standard string, and we're going to initialize a circle with a string. So what's going to happen this time is the constructor is going to go through its, as it always does, go through the potential candidates. First of all, it's going to look at this one. It says, well, this one takes no parameters. You've supplied me with 1, right? So this is no longer a candidate. We'll eliminate that straight away. Then it's going to look at this one. It's going to say, all right, well, the number of parameters matches, so that's a good start. All right, now, can I convert from a string into a float? You've supplied me a string. I'm expecting a float. Is there some way I can do that conversion? And no, there isn't. So this one is going to be eliminated as candidates. And at that point, there are no candidates left. Well, there are, but we will ignore those for the moment. This is going to give you an error that there is no matching constructor for circle, which takes a standard string. Does this make sense to everybody? Getting some good nods around the room, some solid nodding. I like that. Nods mean no. Oh, that's all right. Well, in that case, everybody shake your head when I next ask. In opposite world. All right. So we just saw on the previous example, on the previous slide rather, an example of a class with a constructor taking no parameters. Constructors which take no parameters are special. I have a special name. A constructor which takes no parameters is called a default constructor. Strictly speaking, a constructor which may be called with 0 parameters. Constructor which takes 0 parameters is a default constructor. And these are rather special. In fact, they're one of the what we call the special member functions. And the reason they're special is because if we do not write any constructors ourselves, the compiler will automatically generate a default constructor for us. If we don't write any constructors ourselves, that's the crucial bit. Okay? And what the compiler generated default constructor does is it does pretty much what you would expect it to do. which will be if we have written our in-class initializers, that's like, like we had float f equals 2.17 whatever, it's going to use those values as the initial values of those members. Okay, it's going to use the member initializers, the in-class initializers, as the values. If we have omitted the in-class initializers, then what it's going to do instead is default construct the members. Call their default constructors. So you can see, in a way, this is almost kind of recursive, in that the compiler-generated default constructor will by default call default constructors, which will by default, there's a lot of the word default in that sentence. But again, let's have a quick look at what I'm talking about. So here we have a struct rectangle. It just wraps a width and a height. It's got two getters, get width and get height. You can imagine there are equivalent set width and set height functions that I've omitted just for space on the slide. But again, for those who have done Java or whatever, these getters and setters are really, really common, to the extent that some languages will even generate them for you. C# does, for example, has properties. But in C++, we don't have properties. We have to write the getters and setters ourselves, but generally it's not too hard, as you can see there. Okay, so the first question we want to ask ourselves is rectangle here, is rectangle an aggregate? Why is rectangle, you're shaking your head. Why are you shaking your head? Exactly, yeah. So rectangle is not an aggregate because it has private members. So the width and height here are private, therefore rectangle can't be an aggregate. Does rectangle have any constructors? Okay, so a constructor, a constructor is a special function that is used when we're creating a new object of that type. So these two things are not constructors. They just allow us access to the members.
But is there hidden or default constructor in this case?
Exactly. So remember, the rule is if we do not write any constructors ourselves, the compiler will generate a default constructor for us. In the case of rectangle here, we haven't written any constructors ourselves. Therefore, the compiler is going to generate one for us. A default constructor. Rectangle will have a default constructor, yes.
Can we say to the compiler not to?
You can.
In that case, we can say it's aggregate. Otherwise,
No. There is a way of saying to the constructor, all right, normally you would do this, but please don't. However, that would still not make rectangle an aggregate. Rectangle cannot be an aggregate because it's got private members. Okay?
apart from private.
Yeah. So now we've got a second class window. Well, in this case, imagine this is like a window on your desktop, right? Let's reveal a bit more of that. So window has a name, a title, appears on the title bar, and it has some dimensions, right? It has a width and a height. This has one constructor. It takes a name, and it uses that to set its internal name in here. And you can imagine the window has other functions, again, that I've omitted just for space. Okay. So now what we're trying to do is to construct a rectangle. and we have supplied no arguments. So the compiler is going to, first thing it's going to do is say, is this thing an aggregate? Well, no, it's not, right? So it's going to look for a constructor taking no arguments. And lo and behold, it's going to find one. Because we haven't written any constructors of our own, it's going to get an automatically generated one. So this is going to work. Okay? The next question is, if I write this, what are the values of width and height in this rect object? So, louder, sorry, I can't. 1 and 0, absolutely, yes, well done. So what the compiler generated constructor does is it looks for these things like member initializers, as we see on the width member here. This is something called a member initializer or an in-class initializer. And width has one, so it's going to use that. Brilliant. Height does not. This is bad, it probably should. But it doesn't, so the compiler's going to, well, actually, is it? It's kind of complicated. But it's probably going to give it a value of 0. It's either that or it's uninitialized, and I can never remember which one it is. Because it's not we have not written any constructors of our own, so we get a compiler-generated default constructor. You can double check that on Godbolt for me. So now we're going to construct a window. And we're going to supply a string literal. Compiler is going to say, again, it's going to go through this process. Well, what are the available constructors? There's one available, takes a standard string, can convert a string literal into a standard string. This is going to call it, everything's going to be happy. This is fine. In the body of the constructor, we're setting the name member. We haven't touched the dimensions member. So what's going to happen is that dimensions is going to get default constructed. So again, it's going to go through this process of calling the default constructor, which is going to have the default values, just like we wanted. And now lastly, I'm going to construct a window, a second window, and I'm not going to supply any constructor arguments this time. What's going to happen in this case? Well, it's not going to work. Why is it not going to work? Oh, sorry, a couple of people speaking. What did you?
There's no default one constructed.
Exactly. So window does not have a default constructor. The reason it doesn't have a default constructor is because we supplied our own, therefore the compiler has not generated a default constructor for us, therefore window does not have a default constructor. We cannot try and construct it with no arguments. This is going to give us a compile error. Again, no matching constructor. So, yes, you're absolutely right. The very final thing to say is that the default constructor is one of what we call the special member functions. There are a few of these. We'll get into the other ones later on. But the default constructor is one of the special member functions, and what makes it special is that the compiler can generate it for us. But as we've mentioned, it will only do this automatically if we supply no constructors of our own. However, sometimes, quite frequently actually, we want to write our own constructors, but we want a default constructor as well. Right? So it would be nice if there was some way to say, okay, compiler, usually you won't do this for me automatically, but I would like you to. I would like you to generate a default constructor for me, even though you normally wouldn't. Okay, please could you generate one for me? So normally we only get a default constructor if we supply no constructors of our own. There is a way of requesting that the compiler generate one even if we have written our own constructors. And the way we do that is by using this special syntax of equals default, where we would normally put the constructor body. Instead we write equals default, semicolon. And that is an instruction to the compiler to say, generate this for me, please, if you can. This syntax, this equals default, only works for the special member functions, only works for the things the compiler is able to generate. You can't just chuck equals default on any old function and hope for the best, right? There are only certain things that this equals default syntax works on. Those things are called the special member functions. The default constructor is one of those special member functions.
Just an overload with just no arguments in the brackets. That effective default constructor, rather than having the equals default.
Yes, but there are magic things that happen sometimes if you've got equals, if you use equals default rather than an empty pair of braces. 99% of the time they're the same thing. Yeah. This is explicitly defaulted explicit default constructors. Yeah, it's crazy. So rectangle is as it was before. But this time in our window class, we've added this line, window, empty brackets, equals default. And again, just to reiterate, this is us saying to the compiler, please go ahead and generate a default constructor for me. Please write this for me. Usually you wouldn't, but in this case, I would like you to, please. So we can say equals default.
This does the compiler to generate a default constructor.
That's exactly what it does, yeah. It tells the compiler to generate a default constructor if it normally wouldn't. Otherwise, in this case, it wouldn't. We can also, if we wanted to, we could say rectangle empty brackets equals default up here. That would be fine. It would be redundant because it's going to do it for us anyway, but it would do no harm, if you see what I mean. So we have these things as before, but in this case now, well, we're going to get the same process that I talked about a couple of slides ago. Compiler's got multiple constructors it can consider. Well, this one's out because it's expecting a parameter and we haven't supplied any. This one matches, 0 parameters. And so it's going to go ahead and use the compiler generated default constructor. So this is now okay. So last time out, I kind of left people with this little exercise. I won't go over this now. I will leave those on the slides for people to look at as their leisure because we have to move on. And, well, we're going to come back to this little exercise anyway, so we'll get a chance to look a bit more at it in a little bit. But from now on, let's move on to talking about something new. Let's talk about explicit constructors. And in particular, let's talk about implicit conversions. So I've already mentioned this process of what we call overload resolution. This is when we call a function, we want to match, the compiler wants to match the arguments we supply, the types of the arguments we supply, match them to the correct types of the function we're trying to call. And again, we've already seen an example. If the types are not an exact match, the compiler will do its best to convert the arguments we supply into the parameter types that the function is expecting. So, very simple example. We've got a function called halve, takes a float, returns that float times 0.5. Well, we can call this with an int just fine, because the compiler can automatically convert an int into a float. So what the compiler is going to do is going to say, okay, you want to call a function called halve. You've supplied me with an int. It's going to look at any possible overloads of the halve function. In this case, there is only one. It takes a float. It's going to say, okay, you've supplied me with an int. This thing needs a float. Do I know how to convert from an int into a float? Yes, I do. Brilliant. So it's going to convert this 4 you give me into a float of value 4. It's going to do that times 0.5, and it's going to return a float of value 2. This is fairly straightforward, I hope. Again, this is overload resolution doing what you expect it to do. The trouble is, sometimes it tries a little bit too hard to make us happy. The compiler tries really, really, really hard. It's like that little puppy that just wants to please you. I'm the first person in history to make an analogy between a C++ compiler and a cute little puppy. Anyway, the compiler will try really, really, really hard to find a matching function if it possibly can. And sometimes it will try a bit harder than we actually would like it to. Because one of the things it will try and do, is to look at the constructors of the parameter type. So if the parameter type has a constructor, so we have an argument that's of, say, an int, and the parameter is some type that has a constructor taking an int, the compiler is going to go ahead and automatically call that constructor for us. If the parameter type has a matching constructor which may be called with one argument, this is a special rule for constructors, single argument constructors, then the compiler is going to use that to perform a conversion for us. Something we call an implicit conversion. And actually this is kind of a good thing. And we've actually already seen this happening. We've seen it occurring. We don't actually, it's implicit, so we don't actually, it kind of happens behind the scenes, but we've seen it in action. So here we've got a function called say hello. Takes an argument of type standard string, and all it does is print the word hello followed by the name, followed by a new line. So create a string variable, Tom, and then we can call say hello Tom, and this is all just fine. This function expects a string, we're supplying a string, hunky-dory, everything works as you'd expect. Well, we can also do it like this. We can call, instead of creating the variable separately and copying it into the function, we can just create the standard string sort of all in one line like that, and pass this string, which wraps Ollie, into our say hello function. So here we are we are constructing a standard string, and we are sending that to our say hello function. And again, this is going to work as we'd expect it to. The funny thing is, we can also do this. So the variable Michael here has a funny type. It's a pointer to an array of constant characters. It's not a standard string. This has a different type. I've used auto there because I couldn't be bothered to spell it out. But the point is, this is a string literal. It is not a standard string. And yet, we can call say hello and pass this variable Michael, and it all works perfectly happily. And the reason it works is because this type, const char star, is implicitly converted into a standard string. And the reason that works is because the string class, has a constructor which takes a string array, char array, as a parameter. So what the constructor what the compiler is doing here is saying, okay, say hello wants a string. You've supplied me with this const char star thing. Is there any way I can convert from a const char star into a string? And actually, yes, there is. All I have to do is call this string constructor. Wonderful. So this is going to, behind the scenes, call a string constructor for us. And the end result is that this line here is exactly equivalent to if we had said this. Well, imagine Michael without the quotation. It's not actually completely identical. It's a typo on my part. But effectively, what is happening is the same thing that happened here, that we are creating a temporary standard string, and we are using that for the duration of the say hello function, exactly as happened with the example with Ollie. So this implicit conversion is actually great, right? It lets us use string literals, and we don't, and we can interoperate with standard strings, and everything's good, and everything's fine, and everything's great. Implicit conversions, yay. Brilliant. Maybe. Let's have a look at a very similar example. We're going back to our circle class now. So again, this is the same circle class or version of it that we've been using for quite a few sessions now. And we've got one constructor which takes a float, uses that to set the value of the radius member, private member, and we've got a getter function there as well. And we've got this function, non-member function, called print radius. Takes a parameter of type circle, or in fact reference to a const circle, and all it does is call the getRadius function and print out whatever that is, followed by a new line. And again, this shouldn't be surprising to anybody at this point. So we can construct a circle with a radius of 4.2, call print radius, pass this circle we've just created, and it's going to print 4.2 followed by a new line. Well, that's great. That's exactly what we want to happen. Again, just like on the last slide, we can do it all in one line if we like. This is going to create a temporary circle, and it's going to call this function with our temporary circle, and it's going to print, again, 4.2 followed by a new line. Everyone with me so far? This is the magic bit. we can do this. Because what's going to happen in this case is the compiler's going to say, all right, you want to call a function called print radius. My only candidate is expecting a circle. You've supplied me with a float. Is there any way that I can convert from a float into a circle? Oh, yes there is. Yes there is. I can do it. All I have to do is call this constructor here. Perform an implicit conversion for you. That's obviously what you wanted me to do. Right? This will work just fine, and it's equivalent to the line above. What it's going to do is it's going to, like I say, the compiler tries really, really hard to make you happy. And it's going to say, well, obviously what you wanted to do was to, like, behind the scenes do this, like, hidden constructor call to constructor circle. And from there, we're going to call the print function, it's a print radius function, with this circle that I have created behind the scenes for you. Yeah.
But why would you do that? There's the print radius function defined.
There is a print radius function at the top there, taking a circle.
It's too far away. I need better binoculars.
There are plenty of seats at the front. So this works. This works, and it's a bit weird and a bit unexpected and a bit surprising that it works. But actually, it's exactly the same rule that we just saw with strings and string literals, right? Behind the scenes, it's performing an implicit conversion for us. It's calling this constructor because it's trying really, really hard to make us happy, to try and let us call a print radius function. The only candidate that it's got expects a circle. Can it convert from a float to a circle? Yes, it can, by making use of this single argument constructor here.
If you had two classes, identical classes, one big circle, one little circle,
Yeah.
and you called both have the radius.
That would be ambiguous overloads in that case.
And if you have a constructor with two parameters, and you pass two parameters to print radius, because the compiler will find the new constructor is
No, no, no. This implicit conversion only happens with single argument constructors. Yeah.
you get two functions.
So this is kind of bad, right? Because this is really surprising that it's kind of behind the scenes calling a constructor for us. Because in this case, the constructor does something really simple. But actually, it could do something, it could, in principle, perform some quite expensive work in the constructor. You know, it could go and allocate lots of memory, or it could go and like do some network communication or whatever. Like constructors, there's no limit to what you can do in a constructor. It can do anything that an ordinary C++ function could do. So having these constructors called behind the scenes is, well, questionable, I think. And it's actually a little bit worse than this, because we can actually call print radius with an int, and it still works. Because now what the compiler is saying is, all right, look, I really, really want to help you out here. So what I'm going to do, I can see how this works, right? If I convert the int into a float, which is like a built-in conversion, convert the int into a float, and then send that float into the circle constructor, well, then I'll end up with a circle, and then I can call the function for you, and then you're going to love me, right? This is forming something we call an implicit conversion sequence. Fortunately, there are limits on the length of this sequence, right? Otherwise, it would really, really get out of hand. It will only ever call one constructor. But anyway, this is mental, that we can call print radius with an int. Right? That's silly. We don't want that. We don't want that at all. Unfortunately, there's a way that we can avoid that. So I would say, well, I've said surprising and unexpected. That's me being a bit kind, really. Crazy would probably be a better way of putting it. Silly. And the reason it happens is, as I say, because the compiler is using the circle constructor that takes a single argument of type float. The compiler is using that to perform this implicit conversion behind the scenes for us. Single argument constructors, like that one, by default are candidates to be used for an implicit conversion. Fortunately, we can opt out of this. We can opt out of being a candidate for an implicit conversion. And the way to do that is by using this new keyword, explicit. And if we use the word explicit on a constructor, then that constructor will not be considered when the compiler is trying to form one of these, what we call implicit conversion sequences. Right? If we write the explicit keyword in front of our constructor, that constructor cannot be used to form an implicit conversion. And that's good. The overwhelming majority of the time, you do not want implicit conversions. They are bad. They result in unexpected functions being called, things compiling when they shouldn't, much confusion and scratching of heads. This is one of these cases that really C++ has the defaults the wrong way around. By default, something is a candidate for an implicit conversion, and you have to opt out. I think it would be, implicit conversions are good sometimes, like we saw with the string and string literal case, that's nice. But it should be the other way around, really. Explicit should be the default, and we should opt in to being, anyway. This is the way it is, so this is what we have to live with. The takeaway, the thing you should remember, the thing that's just should be in your mind, and in fact, if you use CLion and recent versions of CLion will remind you about this by default. Whenever you have a constructor that takes one argument, or can take one argument, it should be marked as explicit, unless you know what you're doing. Get into the habit of marking all single parameter constructors with this explicit keyword. That is just, I very rarely use the word always and never in C++ because there are, or when I'm doing these, because there are exceptions to almost, to pretty much every rule. This is one of those rare cases where I'll say like, explicit is the default, should be the default, should be your default whenever you write a constructor that takes one argument. And only omit it if you really know what you're doing. So here's our circle class now. As it was before, the only difference is I've put this new keyword in front of the declaration of our circle constructor. I have said, okay, this constructor is an explicit constructor. That's the only difference. We can still construct an circle from one argument. That works just as it did before. And again, we can do it all on one line. We can explicitly construct a circle and pass that to our print radius function. What we now cannot do is implicitly construct a circle. What's going to happen now is the compiler is going to say, as it does before, right, is there any way I can, you've given me a float, I'm expecting a circle, is there any way that I can convert this float into a circle? And now there isn't, because the only way it could possibly do it is by using this constructor, which is now marked as explicit. So it cannot use this to try and do the implicit conversion anymore. So we can no longer, happily, we can no longer call print radius directly with a float. And of course, we can't call it with an int either. This is a good thing, right? We don't want these to work. We want these to be errors. So by marking the single argument constructor as explicit, we can prevent the compiler from doing these behind the scenes, surprising, potentially expensive conversions that we are hidden from view, that are implicit. Yes, in rare cases, it's a good thing. You know, again, the string literal thing being the canonical example. In rare cases, it is a good thing, though those are the exception rather than the rule. The rule, the thing to remember, whenever you write a constructor that can take one argument, write it as explicit. You can write explicit on other constructors that take multiple arguments, or even default constructors if you want. Doesn't really do any harm, but its main use is on single argument constructors. Okay. Having ranted about implicit conversions, it's time for you guys to have fun. Yes, sir, thank you. To have some fun. So, for those not many of you were here last time, but last time we had these two classes. We had an exercise that involved these two classes: a struct person and this more complicated class person list, which is kind of a wrapper around a vector of person. So given this code on the right, or if you were here last time, you can use your own version of this because you would have ended up with something very similar. I want you to do these two things on the left, and I'll give you a little bit of time to do that. And then, yes, as always, if you have any problems, if you get stuck, if you don't know where to start, then raise your hand, and me or Ollie or Alex will come and help you out. Yes.
Semantically, we also call it implicit conversion, but has nothing to do with what we just saw. Right? There's no constructor code under the hood.
No, that is something that's built into the compiler. Yeah, and there's no way to disable that
It's
actually.
also the same as when, for example, a function takes a const ref to something,
Yep.
but we actually pass it a variable.
Yep.
But const ref is also a different data type.
Yes.
So strictly speaking, we're passing the wrong thing as well.
Uh,
Under the hood to a const ref.
yes.
In some sense, right?
Yeah, that's a good way of thinking about it. It's like sort of yes.
Because I mean, it's actually different.
Yeah. No, it's a good way of thinking about it. And actually, that is a good point, because if you have two overloads, one of which takes a const ref and one of which takes a mutable ref, right? Then actually, which one gets selected depends on the constness of the variable, right? Because those two are, like, it chooses between overload resolution, and if you pass it a non-const variable, it's going to go, oh, the mutable reference is a better match. Yeah. So yeah, that's a really good way of thinking about it, in fact. And if the rest of you didn't quite get that, don't worry. That was a bit hand-wavy without being able to write it down, but yes. Okay, so yeah, have a go at that for sort of 10, 15 minutes, and if you have any problems, let me know. So I know some of you are still hard at work on that, but we do have a bit more to cover, so I'm going to have to move on. But by all means, if you're coming along on Thursdays, everybody's very much encouraged to do so. Come on Thursdays. We had the workshop session down on the ground floor here, very informal, sort of drop in, drop out, tune in, whatever the phrase is. No, just it's very informal. It's not like this. It's not like lecture style or anything. Just come along, bring a coffee, sit at the ground floor with your laptop. Ollie will be there. He can help you out with any problems you have. It's designed for people to come along and work on problems like this or whatever they feel like bringing to the session. Anything C++ is fine. So if you want to carry on working on this, then Thursday would be a great time to do it. I do have the solution there, but I'm going to quickly move on from it so as to not ruin it for you all. And I'm going to move on to talk about member initializer lists. Again, as I mentioned at the start, this is something that is kind of peculiar to C++. As far as I know, no other languages have something like this. So again, even if you're Java or C# expert and you're like, oh, I know all this stuff, it's all the same, this is something that's a little bit different. I know, I feel you. So first of all, let's talk about member initialization, which is a lot of what we've been talking about and sort of a lot of the point of constructors in the first place, right? So let's look at another iteration of a rectangle class. So this is no longer an aggregate like we have had in previous versions of it. This time we've written a constructor. It takes 2 parameters, so we don't have to bother making it explicit. Takes 2 parameters. And what it does is inside the body of this constructor, it sets width to, or the width underscore member, to whatever the supplied width was, and sets the height to whatever the supplied height was. Right. This is, hopefully, you'll see what's going on in the constructor. Yeah? This makes sense. This is the way you would do it in, something like C# or Java. I have, just for the purposes of clarity, named these things with underscores. That's my own personal style of doing it. You could omit the underscores and you'd have to say this arrow width. But anyway, this way you don't have to worry about that. And now we'll go back to our window example that we were looking at earlier. So in this version of window, we've got a constructor that takes 3 parameters now. A width, a height, and a name. This is, again, you just imagine this is like a very simplified version of like a window on your desktop. I've included this because this is something you might not have seen before, and Keynote has done something funny with the formatting. Those should be 2 identical normal quotes. But this is a default parameter. So this particular constructor can be called with 2 arguments, or it can be called with 3 arguments. So if we call it with 2 arguments, then it's going to use this default parameter. And this is not special for constructors. You can do this for any old function. But you do sometimes see it with constructors. And it's kind of an alternative. An alternative way of doing this would be to define 2 separate constructors, one of which takes 2 arguments, one of which takes 3 arguments. But this kind of saves you a bit of work by having a default parameter. And again, really, that's not the kind of point of this slide, but I just sort of put it on there in case you hadn't seen it before. So what this constructor does is we've got this name member, and it sets the value of that from the argument we were given, or possibly not given, if it uses the default empty string. And then we've got this member of type rectangle, which we've called dimensions, and it sets the dimensions, it creates a rectangle from the width and height. So this is going to call this constructor over here. We're going to create a rectangle, and then we're going to assign that value to our dimensions member. So is it clear to everyone? This is nothing new other than the default parameter. There's nothing new on this slide. Yeah. You could not have a default width. So you have to start with defaults on the right and gradually move left, if you see what I mean. Yeah. You could not have int width equals 0 and then height with no default parameter and then name with a default. Yeah, no, that is correct. But as I say, there is nothing new on this slide, right? No, not so far anyway. This is just a slightly more in-depth example than we've seen so far. So now let's create a window. I'm going to create an 800 by 600 pixel, we imagine, window. And we're going to call it My App. And this is going to pop up a window on our desktop. 800 by 600 pixels with the title My App. Isn't it? No. No, it's not. This, in fact, is going to be a compile error. Why? Yeah, that's the question, isn't it? Well, the error you are going to get is this. No matching function call to, this means a rectangle constructor taking no arguments. The compiler doesn't add the question, the question mark, exclamation mark. That was my editorializing. But actually, this is copied and pasted from the actual compile error that you get if you try and compile this code. And that's kind of weird, isn't it? Because at no point here are we trying to default construct a rectangle. That's strange. So what's going on? Why are we getting this error? Why is it doing this? Why is the compiler trying to default construct a rectangle in the previous example? Well, C++ has a very strict rule, an inviolable rule, that it's something, one of the rare things that you can always rely on. And that strict rule is this. By the time we reach the body of the constructor, all of the member variables have already been constructed. This is a cast iron rule. It's very important. By the time we reach the body of the constructor, all of our member variables have been constructed. Guaranteed. Another way of putting it is that the control, that is where our program is, only proceeds into the constructor body once all of the member constructors have finished what they have to do. Right? By the time we reach the body of our constructor, all of our members are ready for use. This is good. Well, usually good. It's a very simple rule to remember, at least. And one of the things that this means is that if we say something like, this is what we had in the body, rect equals rectangle, so we're creating a new rectangle and assigning that to our rect member. If we do that in the constructor body, this is actually an assignment operation. We're not constructing the rect member here. because rect has already been constructed, what we're doing is assigning to it. So put the previous slide back on the screen. The rule that we have to remember now is by the time we reach the body of the constructor, that's by the time we're inside this bracket, this curly bracket, all of the member variables have already been constructed. They exist. Their memory has been allocated or whatever needs to happen. Their constructors have called, their constructors have constructors have been called, their constructors have finished. So, when we construct our window, or when we attempt to construct our window, what happens is that before we reach the body of the window constructor, the compiler is going to have gone and constructed our member variables already. It's going to construct string, to construct name, first of all, the standard string. Well, string has a default constructor, that's fine. Calls the default constructor, no problem. And then it's going to try and call the default constructor of rectangle. And that's where it has the problem. Because rectangle, does rectangle have a default constructor? Somebody say yes. No, no it doesn't. Why does a rectangle not have a default constructor? It's not hidden, it just doesn't exist. Right? The compiler doesn't generate one for us because we supplied our own constructor. So the compiler's not going to generate one for us. We haven't asked it to. We haven't written our own. There is only one constructor that we've written, and it takes 2 ints. So we cannot default construct a rectangle. But that is what we have asked to do. Because the rule in C++ says by the time we reach the constructor body, all of the member variables have already been constructed. Default constructing a standard string is no problem, right? That works. It's an empty string. Default constructing a rectangle, as we have written it here, is not going to work. And that's why we're getting this error, no matching function call to this is a way of writing the rectangle, the name of the rectangle constructor. That's why we're getting that error. The compiler needs to construct the rectangle member before it runs the body of the window constructor. So there are a couple of ways that we can fix this, or work around it, perhaps. Can anybody think of a way that we could avoid this error? We could make this code work. If I go back to the code.
You could write a constructor for window which initializes
So, yeah, the simplest way to do it is we could add a full constructor to our rectangle class. That would solve this really nicely. So rectangle, empty brackets, we could write it ourselves, we could say equals default, doesn't really matter which one we do. Either way, it's going to add a default constructor to rectangle, and then this is going to work, right? That's one alternative. There is another alternative.
Initialize the private members?
Sorry?
Initializing the private members?
Initializing the private members. Yeah, we could add what we call an in-class initializer here. That's the other way, or another way that we could solve this. So, yes, as pointed out, we could add a default constructor to the rectangle class. Or we could use an in-class initializer for the dimensions member. So in the window definition, we could have written rectangle dimensions, and then, yeah.
I was wondering, is there a way to check whether or not the variables have already been constructed in the constructor of another function, and if not, then just skip that part?
Is there a way to check whether the variables have already been constructed? No. Once you reach the body of a, the members will already have been constructed, guaranteed.
you don't need to check.
You don't need to check. So yeah, two ways of doing this. We could add a default constructor to the rectangle class. We could use an in-class initializer which says, okay, well, just call the constructor and pass 2 zeros. Two alternatives. But neither of these alternatives is great. And the reason for that is we go back to the code for a second. Well, look at what we're doing. We need all of our members to be constructed by the time we enter the constructor body. So we're going to default constructor name. We are somehow going to construct a rectangle as well. And then as soon as we enter here, we're immediately going to, that should have an underscore after it, by the way. Sorry, just noticed that. We're immediately going to override the string, and we're immediately going to overwrite whatever dimensions, whatever the default width and height are. Now, possibly in this case where it's only a couple of ints, well, that doesn't matter. But in general, we're going to call a default constructor, usually. We're going to fill the class with like dummy values, and then immediately in the constructor body, overwrite those dummy values. And that's kind of not great. That's doing a lot more work than we actually need to. And for this and other reasons, C++ lets you avoid this using something called member initializer lists. So in a constructor, and only in constructors, there's a special syntax for something called a member initializer list. And the member initializer list lets us tell the compiler how to initialize class members. Probably get that from the name. This also applies to base classes that we'll talk about in a couple of weeks' time. So the member initializer list occupies a sort of funny place because it happens, or it's literally placed in the source code, but also conceptually where it happens when you're running this code, is that it does its work before the constructor body. So remember, by the time control, the point of execution, reaches the constructor body, the members have already been constructed. Well, the member initializer list says how to do this. So let me show you what this looks like. So this is the same constructor we had before. 2 ints and a defaulted standard string. And this is the new bit. So I've put the stars there to alert you. This is the new bit. This is a special syntax that only works for constructors. And this is something called the member initializer list, or member init list. I'll actually just fill in the rest of the code because it'll make it easier. So we've got our 2 private members just as we had before. But what this is saying is, okay, I know you need to initialize the name member. I know you need to initialize the dimensions member. I want you to initialize name, underscore, that's the member name, from whatever we were given. And I want you to initialize dimensions, rectangle, from the width and height we were given.
Can this be done in one line?
Yes, I mean, you still need the comma there, but you could do it in one line, yes. I just put it on 2 because actually that's generally... No, as usual in C++, it's not very fussy about white space. You know, you could leave 10 blank lines there if you wanted to. The compiler wouldn't care. But it is most common to actually put them on separate lines. But again, that's a style thing, and you can have many arguments about style in C++. But the important bit is this. This is what we call a member initializer list. And it appears in between the closing brackets or the declaration of the constructor, but before the start of the constructor body. That's these empty braces here. You write a colon, and the syntax is we write the member name and then the constructor, or the arguments that we want to call the constructor with. And this tells the compiler how to initialize the members. So this is going to call the string constructor that takes a string, the strings copy constructor, and it's going to call the rectangle constructor which takes 2 ints. And it's going to call that constructor with the width and height we were given. So we are no longer doing more work than is necessary. Previously, we were creating these things with dummy values and then immediately overwriting those dummy values, which is kind of pointless. Now we're no longer creating those dummy values at all. We're creating, let's say, the rectangles directly with the values we want them to have straight away at the point that they are constructed. And this is better. This is much better. In fact, this is really pretty good. By using a member initializer list, we're directly setting the right values for the 2 members at the point that they are constructed. And actually, that was all the work that we were doing in the constructor body before. We've moved it into the member init list. So you saw in that example, the constructor body was actually empty. Right? There was no work left to be done in the constructor. We did it all on the member initializer list. And in fact, this is extremely common. This is really, really, really common. That constructors will use their arguments to set the members in the init list, and the actual constructor body will be empty. You'll see that a lot in C++ code. Whenever possible, there are some cases where you can't do it, but whenever possible, you should prefer initializing your members using the member init list rather than doing this 2-step thing of default constructing them and then in the constructor body overwriting them, overriding those values that they've just been created with. Member init lists are great. Use them all the time, is what I'm trying to say. Do things in a constructor body only when you actually have to. Oops. So, one of the questions I was anticipating, it didn't actually come up. But one question I had last time we went through this is, well, if you have an initializer list in a constructor and you give a variable an in-class initializer, what happens? And the answer is this. If the member is mentioned in the constructor initializer list, that's that thing with a colon after the constructor, before the constructor body. If a member name is mentioned there, then those arguments are used to call the appropriate member constructor. Otherwise, if a member name is omitted from the member init list, the compiler is going to try and use an in-class initializer if you have supplied one. If neither of those conditions hold, then the member is going to be default constructed, if possible. That is, if it has a default constructor. So there's...
So in the first case, compiler will just keep the row if we
Keep the row.
skip the row. I'm sorry, it was, as you said, so if you, for example, constructed, what is the name of the class in the code that could remember this?
The window and rectangle.
Yeah, if you decided to construct rectangle initializer list and then assign something to rectangle the same parameters.
Yeah.
So now I will skip that line.
No, in that case, so again, the member variables are always constructed before the constructor body runs. And the initializer list lets you customize how that happens, basically. By all means, if you want to, you could write something in the initializer list and overwrite it in the constructor body, but why would you do that? That would be kind of pointless. But you could do it if you wanted to. Sorry.
But if you have, for example, also like a private radius, like a private member variable,
Yeah.
that is also equal to 0.
Yes. So that would be an in-class initializer.
That we, okay.
So we can override that in-class initializer by using the member init list.
Okay, so in that sense, I think that's what you were asking.
This will perhaps be a bit more obvious if I show you an example of what I mean. Perhaps. Let's see. Might generate more questions. All right. So now we've got struct example. The constructor taking one argument, make it explicit. Remember that. I should have put the member variables first, actually. There they are. So this is a struct, or class, doesn't matter. Struct has 3 members: a string, a vector, and an int. And we've got 3 constructors. One that takes a string, one that takes a string and an int, and one that takes no arguments at all. So let's construct one of our example objects and pass the string or the string literal goodbye. First thing that's going to happen, the compiler is going to try and decide which constructor to call. So is it going to call constructor A, constructor B, or constructor C? It's going to call A, right? Because that's the only appropriate candidate. So A, constructor A, this one up here, it has a member initializer list. And this member initializer list says, I want you to construct my str member as a copy of the string we were given. And I want you to construct my I member with the value 42. There's also this vec member. Now, a vec member is going to be constructed. Don't worry about that. It's always going to be. It has to be. But we didn't mention it in the initializer list. So what's going to happen is that vec, in this case, is going to get default constructed. That is, it's going to be an empty vector. So what's going to happen is that after this happens, after the constructor is run, the str member of ex1 is going to be set to goodbye, the vec is going to be empty, and I is going to be 42. Does that make sense? People see why that's happened? Good.
You're using default constructor of vec.
Yes. Okay. So now we're going to construct a second one. This time we're supplying 2 arguments, farewell and 99. So it's going to select this second constructor. This second constructor also has an initializer list. So once this line has finished, once the constructor has finished doing what it needs to do, what is the value of ex2's str member? Sorry? It's going to be farewell, absolutely. Because in the initializer list, we've said, OK, I want you to construct str using the string we were given, which in this case was farewell. Excellent. What's the value of its vec member going to be? So vec is going to be set to 1, 2, 3. because that's what we've asked for in the initializer list. What is the value of a ex2.I going to be? Well, first of all, is it mentioned in the initializer list? No, it's not. So we're going to use the in-class initializer, which in this case was 0. Why have I said 99? Because that was a typo on my part and I'm an idiot. Oh, I shouldn't do these late at night, should I? I don't know what I was thinking there. Possibly I had in mind doing something different in the constructor to what I ended up doing. Never mind. Let's fix it. Finally, let's call example constructor taking no arguments. Now in this case, it's the default constructor. This one, the compiler generated default constructor. So we actually already know what's going to happen in this case. This one, the way you can think of it is it doesn't have an initializer list. So it's going to look for the member initializers if possible. So I'm a little bit worried I might have got this one wrong as well now. I shouldn't do these late at night. But basically, it's going to use the member initializers if they exist, and if not, it's going to default construct stuff. So in this case, str is going to be set to hello, vec is going to be default constructed to an empty vector, and I is going to be set to 0. So we are at time, but there is one very important last thing that I don't want to leave hanging because this is really, really, really important thing to know about initializer lists. So apologies, I'm going to keep you like 2 more minutes. But there is one very, 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 very important rule that you must be aware of. And that is, again, it's one of these absolute cast iron rules that always happens. Member variables are always constructed in the order that they appear in the class definition, from first to last, in that order, no matter what. No matter what. In the order they appear in the class definition. So go back here. It's always going to construct str, followed by vec, followed by I, always, always in that order, no matter what. Not in the order that they appear in the member initializer list. It is possible and strongly inadvisable that you can write things in the member init list in a different order to the order that they appear in the member variables appear in your actual class definition. Don't do it. To avoid confusion, to avoid possible problems, always write your names in the init list in the same order that those names appear in your class definition. You can omit certain names if you want, but don't reorder them. And in fact, modern compilers will warn you if you don't do this, right? But this is something that's very important to bear in mind because you can get yourself into difficulties if you forget this rule. And I am out of time. But just to show you what I mean by potential difficulties, if you weren't aware of this rule, you might look at this and go, okay, we've got 2 members, a vector member and a string member. What I'm going to do is I'm going to construct str from the thing we were given, and then I'm going to initialize vec from my string member. So vec should be a vector of strings there, sorry. Like I said, late at night, shouldn't write. But in fact, this isn't going to work, because what's important is the order that these things appear in your class definition. So vec is always going to be constructed before str. So in fact, these two lines are going to happen in the opposite order. So we're trying to construct vec out of a string that doesn't yet exist. And that's going to cause you big problems. That's like undefined behavior. That's mad craziness, right? Luckily, the compiler will warn you about this. It's going to put up a big red flag and say, no, you're doing something silly here. But that's the reason that this is one of these always things, one of these rare always in C++ things, right? Always write the variables in the initializer list in the same order that they appear in the class definition. Do not ever do this. That's what I'm trying to say.
Is that compilable these days as well?
I might have mentioned that once or twice. Yes. All right. This is like a take-home. I said exercise. It's kind of a take-home thing. It's basically takes something pretty almost exactly what we had before. I want you to start using member initializer lists, as you might imagine. So if you want, you can, I'll leave this on the screen as you file out. If you want to take a photo of it, or I will, I promise, probably, if I remember, put the slides up. So I'll leave you with that. Apologies for taking up an extra 5 minutes of your valuable time, but I couldn't leave it because that last bit is very important.
Let's go to the end of the video on YouTube.
Sorry. Oh yes, and the video is on YouTube right this moment. Hello to everybody who's watching. So yes, you can just scroll right to the end and you'll be able to see this as well. Anyway, that's it from me. As usual, we will be going for a light refreshment afterwards, and everybody is more than welcome to join us at a local establishment for a beverage. Other than that, thank you all very much. See you in a couple of weeks' time. Cheers.